Here's something to chew on. Say you want the average weight of an apple from an orchard. You can't weigh every apple, so you grab a handful, 10 of them, and take the average. Your friend grabs a different 10 and gets a slightly different average.
Right, and a third person, a third average. The thing you computed, the sample average, isn't a fixed number. It jumps around depending on which apples you happen to grab.
So the average is itself kind of random, and that feels like a problem. How can you trust a number that wobbles every time you take a new sample?
That's exactly the question this lecture answers. It turns out that wobble has a beautiful, predictable shape. And once we know the shape, we can put real numbers on how much to trust a sample. Today, the Central Limit Theorem, and then 2 more curves it opens the door to, chi-squared and t.
Let's name what we just described. Each time you take a sample of size m and average it, you get one value of x bar, the sample mean. X bar equals x1 plus x2 on up to xm, all divided by m.
And here's the tension. Last lecture's law of large numbers told us that as the sample grows, x bar settles down toward the true mean mu. But for a fixed sample size, your one handful of 10 apples, x bar is still spread out around mu. The question is, spread out how?
And that's not a side question. It's the whole game. If we know the shape of how x bar is spread around mu, we can attach actual probabilities to a sample result. That's the heart of statistics, going from one sample to a statement about the truth. So here's the answer, and it's the most important result in the whole subject. For a sample of size m from a population with mean mu and standard deviation sigma, when m is large, x bar is approximately a normal curve, centered at mu, with a spread of sigma over the square root of m. And we can say it the standardizing way too. Take x bar, subtract mu, divide by sigma over root m, and that quantity approaches the standard normal z, the same bell curve we've been reading off a table all week.
And here's the part that should genuinely surprise you. The population you sampled from can be any shape. Skewed, flat, even 2 humps, doesn't matter. The distribution of its average still comes out normal. That's why it's called central. It's a law that sits at the center of everything.
Let's look harder at that spread. X bar is centered at mu. Good, it's aiming at the right place. But its standard deviation is sigma divided by the square root of m. That quantity has its own name, the standard error.
And the square root is the key. Because you're dividing by root m, the spread shrinks as the sample grows, but slowly. To have the standard error, you don't double the sample, you have to quadruple it. 4 times the data buys you half the wobble. You can see it in the picture. Small samples give the wide gold curve, big samples the tall, narrow wine one, both centered on mu.
So the theorem says for large m, but how large is large? Is there a rule?
The rule of thumb is m of at least 30. 30 or more and the normal approximation to x bar is good, as long as the population isn't wildly skewed.
And what if you have fewer than 30?
Then it still works, provided the population you're sampling from is already roughly normal to begin with. Small sample, but a well-behaved population, and you're fine.
So there's a trade-off. The more symmetric the population, the faster the sample mean turns normal. A nice population needs almost no help. A lopsided one needs a bigger sample to smooth out. Let's make it concrete. Light bulb lifetimes have a mean of 800 hours and a standard deviation of 40 hours. We take a sample of 16 bulbs. What's the chance the average lifetime comes out below 775?
First, the standard error. Sigma over root m is 40 over the square root of 16, 40 over 4, which is 10.
Now standardize the boundary. The probability x bar is below 775 equals the probability z is below 775 minus 800 over 10. That's minus 25 over 10. So the probability z is less than minus 2.5.
And from the normal table, the probability z is below minus 2.5 is 0.0062.
So a sample average below 775 is rare, only about 6 in 1,000. Notice what we did. A single bulb varying by 40 hours is ordinary, but the average of 16 has a standard error of just 10, so it almost never strays that far. Averaging tames the wobble.
Before we move on, why is this one theorem such a big deal? 2 reasons.
First, it explains something from earlier this week. A binomial count is just a sum of m yes or no trials, which is a scaled average. So the CLT is exactly why the binomial starts looking normal for large M. That wasn't a coincidence. It was this theorem in disguise.
And the second reason is the whole future of the course. Because x bar is normal, we can say how far a sample mean is likely to land from the true mu. That's the foundation of confidence intervals and hypothesis tests, which is exactly where we go next week. Okay, the CLT handles the sample mean, but not every question is about a mean. Sometimes you care about the spread of your data, or you have a tiny sample and don't know sigma. So we need two more curves.
Two new ones. Chi-squared, that's for the sample variance, S-squared, and the t-distribution, that's for the sample mean when sigma is unknown and the sample is small. The common thread, both are built out of the standard normal z, and both are read from a table exactly like the normal. Find your degrees of freedom row, find your tail area.
One honest caveat before we dive in, though. These two, chi-squared and t, assume the data come from a normal population. That's different from the CLT for x-bar, which works for any population once the sample is large. So keep that distinction in your back pocket. The CLT is forgiving. These two lean on normality.
Let's meet chi-squared. When you study a sample's variance instead of its mean, a new right-skewed curve shows up. It lives only for positive values of x, and it's indexed by a number v, the degrees of freedom. Now here's the one fact to hold on to, and it's a clean one. For a chi-squared curve, the mean equals v, and the variance equals 2v. Mean is v, variance is twice v. That's it.
I like that because v does double duty. It labels the curve and tells you roughly where the center sits. And the picture shows the skew. At v equals 4, it's lumped to the left with a long right tail. At v equals 8, it's already starting to even out.
And here's where the curve actually comes from, the normality assumption made concrete. If you take a random sample of size n from a normal population, then this specific quantity, n-1 times s squared over sigma squared, is chi-squared with v equals n-1 degrees of freedom. So the sample variance, scaled that way, is what rides this curve.
So how do we actually use it? Just like the normal? We read off a cutoff value that leaves a chosen area in the upper tail. We write it chi-squared alpha. The probability x is at least chi-squared alpha equals alpha. You look it up by your degrees of freedom v and your tail area alpha.
And here's the table itself. Rows are the degrees of freedom v, columns are the tail area alpha. You find your row, slide over to your column, and the cell is the cutoff. For instance, at v equals 12 and alpha equals 0.01, that gold cell, the value is 26.217. Row and column in, cutoff out.
Let's read it both directions. First direction, a value, find the area. With v equals 5 degrees of freedom, what's the probability x is at least 8? Reading the table at v equals 5, that comes out to about 0.156.
Other direction, an area, find the value. With v equals 12, find chi-squared 0.01, the value with 1% in the upper tail. Reading the table at v12, alpha 0.01, it's 26.217.
And the table panel shows both at once. For the first one, the value 8 at v equals 5 lands between the 0.20 and 0.10 columns, so the probability is somewhere between 0.10 and 0.20, and the more precise answer, 0.156, sits right in there. For the second, the gold cell at v12 reads 26.217 directly. Same table, read two ways.
Now the t-distribution. This is the one you reach for when sigma is unknown and the sample is small, which honestly is most real life. Let me give you the recipe slowly because the formula looks busier than it is. You take a standard normal z on top and an independent chi-squared v on the bottom. And the full thing is t equals z divided by the square root of v over v. Z over the square root of v over v.
So it's a normal, but divided by something noisy underneath. And that noise in the denominator is what fattens it up. The t-curve is symmetric and bell-shaped like the normal, but with heavier tails. You can see it against the gold normal curve. Same center, lower peak, fatter tails.
And here's the practical version of that formula. The normality assumption again.
If the population is normal, then take x bar minus mu over s over root n using the sample standard deviation s in place of the unknown sigma, and that follows a t with v equals n minus 1. So whenever you'd use a z but you had to estimate sigma from the data, you really should be using a t.
And reading the t-table is, surprise, just like the normal. We write t alpha. The probability t is at least t alpha equals alpha. And because the curve is symmetric, the probability t is below minus t alpha is also alpha. The two tails mirror each other.
Quick, why does this thing even exist aside? The extra spread of t, those heavier tails, is the price of estimating sigma from the sample instead of knowing it. You're less sure, so the curve is wider, so your cutoffs sit farther out. And the payoff, as v goes to infinity, as your sample grows, t alpha slides right back to z alpha. Lots of data, and t becomes the normal again.
And here's the t-table. Same layout. Rows are v, columns are the tail area. Find your row, find your column. Read the cutoff. For example, at v equals 15 and alpha equals 0.05, the gold cell, t alpha is 1.753.
Let's work 1. With v equals 12 degrees of freedom, find the probability that t lands between minus 1.356 and 2.179. It's a between question, so we peel off the two tails. From the t-table at v12, 2.179 is t0.025, so the probability t is above it is 0.025. And 1.356 is t0.10, so the probability t is below minus 1.356 is 0.10.
So the middle is just 1 minus the two tails. 1 minus 0.10 minus 0.025, which is 0.875. 87.5% of the curve sits between those two cutoffs, like the shaded band in the picture.
And the table panel shows exactly where those two cutoffs came from, both from the v equals 12 row. 1.356 is the 0.10 column. 2.179 is the 0.025 column. 2 gold cells, 1 row. Peel the tails, subtract, done.
And if you'd rather not interpolate by hand, GeoGebra's free probability calculator does both of these curves directly. Pick student t, set degrees of freedom to 12, ask for the area between minus 1.356 and 2.179, and it shades the middle and reads back 0.875, exactly our worked answer. Switch it to chi-squared with v equals 5 and ask for the probability above 8, and it returns the exact 0.156, the precise value the table could only sandwich between 0.10 and 0.20. Same answers, no interpolation.
Let's pull the 3 together, because the hardest part on a test isn't the lookup, it's knowing which curve to grab. 3 distributions, 3 jobs. First, the normal z. You use it for the sample mean when sigma is known, or when the sample is big, 30 or more. Second, student's t, also for the sample mean, but when sigma is unknown and the sample is small. That's the everyday case. And third, chi-squared. That one's not about the mean at all. It's for the sample variance, s squared. Different question entirely. So the quick decision, mean or variance? If it's the variance, chi-squared. If it's the mean, do you know sigma, normal, or not? T. And all 3 ultimately trace back to the normal. The CLT really is the thread running through the whole family.
I want to drive that last point home because it's the satisfying part. The normal sits right at the center of this whole family. As the degrees of freedom v grow large, the t-curve slides into the standard normal, and the chi-squared curve straightens out, loses its skew, and becomes symmetric and bell-like.
And the reason they differ for small v is just honesty about uncertainty. A small sample carries more doubt, so t gives you heavier tails and chi-squared gives you more skew. Those are the curves protecting you. As the data pile up, the doubt fades, the corrections melt away, and everything collapses back to the one bell curve. More data, less special casing.
Let's wrap the week. Today was 3 sampling distributions. The headline is the Central Limit Theorem. X bar is approximately normal, centered at mu, spread sigma over root m, for any population. And then chi-squared for the sample variance, and t for the mean when sigma is unknown. both read from tables, both returning to the normal as the sample grows.
And step back and look at the arc of the whole week. We went binomial, to normal, to the normal approximation, to samples and data analysis, and now to the CLT, chi-squared, and t. That's the moment probability quietly turned into statistics. We stopped asking, what will the data do, and started asking, what does the data tell us about the truth?
And that question, what does the data tell us about the truth, is all of next week. Week 4, statistical inference, estimating mu and sigma, building confidence intervals, and running hypothesis tests. Everything we built today is the machinery that makes it work. See you there.